So, I want to talk to you about two things today. The first is directly related to this program, and it is about contracting tensor networks. But unlike what we usually do or what we strive to do, I'll be talking to you about contracting tensor networks that don't have a nice structure. In fact, they might have little to no geometric structure, okay? So even though this is not so common in physics, it does arise as a case in computation and simulating computation, and in particular quantum computation. Secondly, this talk is about solving counting problems, and hence the title Fast Counting. So counting is not, the counting that I'm referring to is not quite 1, 2, 3, 4, but it is more counting with constraints, okay? So we're talking about combinatorial enumeration problems that are hard, but at the same time, it is an important class of problems that crops up a lot in AI, in computation in general, but also in physics, StatMech, etc. So, yeah, a few disclaimers are that this is not your typical tensor network talk. I will not be talking about matrix product states, gauging, DMRG, all that stuff. So there will be no nice geometric structures. There will be no PEPs, no MERA, none of that stuff. Another disclaimer might be, for this audience, there will be almost no physics in this talk, okay? So, nevertheless, I think what I'll be showing you offers a perspective to tensor networks that at least I have found stimulating in the last few years. And so, here's the rough plan for this presentation. We will start with something a bit, strange. We'll talk about logic, okay, to clear our minds of our preconceived notions about tensor networks. And then, in particular, we talk about propositional logic and how propositional logic and inference using this type of logic can be expressed as multilinear algebra, meaning tensor networks. Then we will talk about Boolean satisfiability, or the SAT problem, and how that is expressed as tensor networks. And then also, I should say here, perhaps SAT and sharp SAT. Sharp SAT is the counting version of the Boolean satisfiability problem. And then finally, I will show you some ways of contracting irregular tensor networks. What I mean by irregular is something that might or might not have some geometric structure in it, okay? And then I will apply these contraction methods that I show you to two examples. The first one is some combinatorial enumeration or model counting benchmarks. Okay, and we will take instances, so-called industrial instances of this problem, and try to solve them. And finally, I'll show you also results of applying the same methods to the simulation of quantum circuits. And there we will take as an example the Google Sycamore supremacy circuits. Okay, everybody ready? Yes, very enthusiastic, yes. Okay, yes. So yes, thank you. All right, let's start with logic. So what is logic? Logic is the study of valid reasoning, okay, or invalid reasoning. So we want to make statements like all men are mortal, and statements like Socrates is a man. And from these propositions, as they are called, we want to infer new ones that follow logically. So we have propositions that are premises and propositions that are conclusions of these premises. And we want to make valid inferences, okay? So this is about logical inference. And we want to make it sound, and also we want to be able to detect when a combination of propositions is not sound, okay? So the reason why we want to do this is it might be philosophical, so it might be you know, in the social sciences, but it might also be linguistics, math, computer science, etc. Okay, so this study of logical inference in the Western world, at least, was introduced by Aristotle. But here we will be talking about something that came a bit later, which is called propositional logic. And this was introduced by the Stoic philosophers in ancient Athens, and then a bit later on by George Boole. And the way this works is we have atomic propositions. I promise you this is going somewhere, okay? So don't worry if... or variables. Okay, so P is a proposition that is elementary, and it is a binary variable. And we have logical operators or relations between variables. So this is the problem in its most general form. But just to restrict ourselves to a simpler language, we will consider the following logical operations. I will list them here as a symbol, how we read them, and how we call them. So this is a negation, so we call it not. And this is a unary operator. This is a conjunction, and we read it and. This is a disjunction, and we read it or. So, using the alphabet of variables and these three relations, we can express any formula of propositional logic. And I will do an example in a bit to show you how this is done. Okay? Now, if we have a list of variables, we can put them in a, say, of n variables, we can put them in a vector. So we have an assignment of n variables. So as an example, Boolean variables. Belonging to this set. So we write vectors like this. And it's clear that if we have n Boolean variables, we'll have 2 to the n assignments. Now, given a one more thing. So I said that we can write any proposition in propositional logic using only these relations, variables in these relations. In fact, we can restrict this even more and talk about formulas in conjunctive normal form or CNF for short. And these are conjunctions of disjunctions. So we write a formula, F, as a number of disjunctions and take their conjunction. Okay, so CI, each of these CIs is an OR of some Boolean variables. And so these are called clauses, typically. They're also relations or logical operations. Here, variables can also come in negated. These are variables, and this is a formula. And it turns out any formula in propositional logic can be written in this form. Yes? No, because here I can broadcast the same variable in many clauses. The copy comes in when you put in, when you go to the Tensor Network language. We will do this in a bit. Okay, so one way to write down explicitly what these relations are truth tables, okay? And so you probably know this stuff, but I'm going to write one down anyway. So truth tables. Maybe I should be a bit more organized with how I write. I'll go over there. Okay, truth tables. You probably know what this is, but okay. So we have two variables, phi and psi. And let's take the logical relation or the logical operator. Let's take OR. Let's take OR, yeah. Here we put all possible values of these variables. And remember, these variables themselves are propositions. And the relations that we define between them are also other propositions, okay? So these take a logical value. So this takes a logical value. And in this case, it's the truth table is this. So 0 or 0 gives 0, okay? So I've switched. I take 0 to be false and 1 to be true, okay? It's like a logical, yes? Yes, yes, this could be the case, but it's not necessarily efficient, but basically using this form, you can define important classes of problems. So for example, you can define problems in P, you can define problems in NP, you can define problems that are NP hard using this. Okay, so it is just practical to use it in a sense. Okay, so this is one way to represent propositions and logical relations. Another way is to use, people call those logical matrices, but in fact, if you have a multi-way relation, like in here you have multiple variables, then you promote this to logical tensors. Okay, and logical tensors look like this. So you take A or B, what we wrote here, and in this case, this becomes something like A can take values 0 or 1, and B can take values 0 or 1. And in here, in the tensor, you put the corresponding entry of the truth table. Okay, and if I were to do a three-way relation, just to, because this is a matrix, because we have two variables. If we have three variables, now I would have to write in 3D, okay? But instead, what I'll do is I'll just group here variables A and B. I'll just matricize. And here I will put, T equals 1. And so here I will put the corresponding truth table that I would get, which I have 3 variables, meaning it should have 8 entries. And so I have 0 for this guy and 1 for everybody else. And this is clear, right? Because this becomes false only if all 3 assignments are false, okay? And otherwise it's true. Okay. Here, using this conjunctive normal form, now I can pose a question. Is there an assignment X that makes F true, otherwise satisfies F? Okay, that's the question we pose. And this question is the Boolean satisfiability problem. Okay, so this is a decision problem. The answer is yes or no. There exists or there doesn't exist. And this problem goes from trivial, meaning there are instances of this problem that you can write, that you can solve in polynomial or even linear time, or even more trivial, to NP-complete or harder. Okay, NP-complete is basically the hardest problems whose, sorry? We'll get to that, but it is. Sorry? Well, if here I say, instead of is there, I could say how many, right? So basically, this is a problem whose solution can be verified in polynomial time, but you might need exponential time to solve this problem, okay? Unless something really radical happens in our understanding of computational complexity. Okay. So this is the SAT problem. Okay. Now, we have the problem, we have a computational problem here, and we have a language to express it in, which are these logical tensors. And so let's see how we can do this. We take a Boolean algebra and turn it into a Boolean linear algebra, or actually multilinear. So our operations are done in this fashion, such that 1 plus 1 is 1. The reason for this is that if you take, I'll show you in a second, but basically this algebra works over a semi-ring, okay? So there's no inverse of the addition, but this allows us to express the OR operation as plus, the AND operation as times. Okay, and here we can see how this works. Okay. Okay, so we said okay, so if I take 1 plus 1 to be 1, then my plus is my OR. Okay, and similarly for A and B. B. Okay, so in a sense, I'm overloading, if you're into programming jargon, I'm overloading these operators. And so And so if I am now to do algebra with these relations, I can do what's called composition of relations, which basically goes back to De Morgan. Yes. It's A and B, right? So 0. Yeah. Cool. Okay. So then composition of relations is basically inference. Okay. So we use an algebraic way to do deductive inference. So here's an example. Let's take the formula A or B and not B or C. Composition makes sense mostly when you have a common variable, right? Because otherwise, if you don't have common variables in your clauses, then the composition is like a tensor product, okay? But in this case, I want to ask if there is, or what is the relationship between A and C. So we could do this with a truth table method, but it takes long. Let's do it with the logical tensors. Okay, so let's write the first relation. A or B. Okay, same way as before. Times not B or C. And here I have B negated. So in fact, the unsatisfying assignment is when B is 1 and C is 0. Okay, so I need to put the 0 here and 1 everywhere else. And so now what do? Well, I do matrix multiplication. That's the composition of relations in this case. Why? Yeah, so yes, so I can. Yes, so you want it to be gone because you want to infer whether there is a relationship between A and C based on this formula. Okay, and so okay, we can write down the this matrix multiplication explicitly to show why this is the case, right? So what do? We take the first row and multiply the first column, okay? But what does this tell us? It tells us, let's write this as 0 times 1 plus 1 times 0. What is this? This is basically A equals 0. And equals you can write as again as a composition of ors and nots and etc. Times is end. B is 1. Or A is 1. Sorry. A is 0 and B is 0, sorry. Basically, you put in the relationship. Actually, let me write this in the general way because this will help us see it. For any relation, I can write this. So suppose I have a relation R, and this R can be AND or whatever. So if I write A relation B, again, this is for Boolean variables. This is essentially what I'm writing down. So this is what I wrote before, more formally. So when I write this definition here, essentially what I'm writing is this thing explicitly. That's right. That's it. And in fact, we will do an example, and then we will do a counterexample where in one case, the value of B matters, which is this case, okay? Because if I multiply these matrices, what you find is, and now this is A, and this is C. Okay, and so basically the relationship that comes out of this is that the relationship is, or the relation is A or C. Okay, now if I remove this negation and do the same thing, so first things first. So here what we did is what? It's a tensor contraction. Okay, so we contracted two tensors and we basically made an inference, a logical inference on the free legs. Okay, the free legs are A and C. So this is how to view tensor contraction as logic. No, that's not the reason. Because as we will see, if we do this, it's more subtle. It actually boils down with what I'm about to say next, right? But it's not that simple, because if I did the contraction here, not using this algebra, but actual 1 + 1 = 2, like integers, this problem is sharply complete. Okay, so you need, it's not that simple. It's not because you have just binary relations that the problem is easy. Yes? You could call 2 anything that is non. Yes, you could, but again, the counterexample that I'm about to write illustrates this, the difference, right? Because suppose here we do this formula, sorry, A or B, and B or C. So now the matrices are like this, okay, because we have no negations. And now if I do my my tensor contraction here, what I find is just 1 everywhere. Okay? So what happens here is the rank collapses. And so it means A and C are independent. So not only do you have a notion of the notion of contraction carrying over to inference, but you have the notion of an incomplete rank, meaning independence or redundancy in these problems. Okay, and here, if I did the multiplication, here I would get a 2. In fact, this is what I'm going to do next. Okay? Make sense? So rank in one case collapses, in the other case does not. There is, yes. So, I mean, here it is clear that the rank collapses, right? So there must be. Yeah, so there is. And in fact, you can do Boolean rank decompositions depending on, but the rank in those is not the same as the integer rank. Yeah, so. Okay, great. So now, so we did the logic part. Now let's go to the counting part, and let's allow 1 plus 1 equals 2. Now if we take this formula here, let's call this F1, F2. F2, in this case, evaluates to, or gives rather, this this sort of matrix, and then this entry represents the case where A equals 1 and B equals 1. And so we might ask, for any formula F, we can ask the question, how many assignments does F have? Sorry. How many assignments make F evaluate to true? Or in other words, how many valid assignments does F have? And so this takes us to combinatorial enumeration or counting problems, okay? And typically what happens is you start from an NP-complete problem, you turn it into a counting problem, and it becomes sharp P-complete. This is not always the case. A counterexample is 2SAT, which is in P, and becomes sharp P-complete when you turn it into a counting. So you have decision here. Decision is the other problem we wrote down there, and this is the counting counterpart. And so as an example here, you can take 3SAT and get sharp 3SAT as the counting counterpart. Now, it is really, here you see how nice tensor networks are as a language for these problems, because you can incorporate any formula like this very naturally as a tensor network. Okay. Okay, and that's what we're going to do now. So we'll talk about the graphical representation of formulas. And why graphical? We'll use graphs basically to represent these instances. And well, why graphs and not say some ordered lattice or some nicely structured thing? Well, in many cases, when, for example, you want to evaluate the output of, well, the correspondence of inputs to outputs of a classical circuit. When you want to design a VLSI circuit, like a chip layout, the instances that pop out are actually not ordered. They come out as jumbles of variables and clauses, okay? And what you would need to evaluate the truth value of, or count the solutions of, is actually disordered or irregular as a structure. And so we use this graphical representation There's other problems also that map to these, okay? There's vehicle routing problems, there's decoding of error-correcting codes, etc. So there's a lot of things that map to either decision or counting or optimization, okay? But all of these problems can be expressed in this graph theoretic language. So our relations or constraints are written as one type of vertex that I will write as open. Okay, and the legs are variables. And so, for example, here I could write a relation that is A or B or C. So that gives 3SAT here, like this. Okay, and then now for the variables we need the copy tensors. Okay, if variables. Okay. The copy tensors are if in these formulas I have the same variable occurring on multiple clauses, I need to broadcast its value, okay, to all these clauses, because in this notation, which is called factor graph, my edges are my variables. Okay, so if I need one variable to go to multiple constraints, then I either need a hyperedge, which is something else, or I need a way to broadcast the same value to multiple clauses. Okay, and for this we use the copy tensors. And this I usually write as full. And this is basically a delta tensor. Okay. Now, the formula F is a bipartite graph because variables connect to constraints only, okay, and vice versa. Also, this graph will be connected because it doesn't make sense to look at disconnected graphs. You can look at each of the components, do your count, and then multiply the results to get the total count. And so also there is, for these formulas, typically there are no free legs. No free legs. The legs, I mean variables. And so it means the result is a scalar. In the decision case, it's yes or no. In the counting case, just an integer number. Okay. By the way, counting in this language generalizes even further to weighted counting. In weighted counting, we talk about graphical models and then many partition functions, Statmek of spin glasses, etc. So you can encode that also in this language. And also very naturally, if you do weighted counting, well, then you can add also complex weights and do quantum, okay? So it's very, very general. So if we take, for example, a 3-sat instance, we will have these vertices that are our clauses. Okay, and each clause connects to 3 variables. Okay, so I have a network like this. This doesn't look very random. But anyway, you contract this. Rather, the tensor network representation of this, and you get a scalar, which is your result. A few remarks here. This goes back to my earlier remark that there will be no good algorithms. All the algorithms that I will show you afterwards are bad in the sense that the Sharpie completeness of this problem in general guarantees you that there will be no polynomial time algorithm for contracting these networks, right? Not even approximation works for the hardest problems because there is even controllable approximation for these problems is unlikely because of a thing called ETH. It's not the ETH you know. It's the other ETH, exponential time hypothesis. Would be really fun if these two are connected, but I don't think they are. But in any case, exponential time hypothesis says that basically what I just said. There will probably be no meaningful approximation to a problem like sharp 3-sat. It is. It is.
It's still exponentially hard, but it's much easier.
Yeah, but so when computer scientists talk about approximate algorithms, you want a bound on how far you will get from the exact result. So you want a guarantee that you will be within a range of the exact result. It is what? Yes. It is easier, yeah. Yes. Formally, it is easier, but formally it is easier because you can do, for example, Stockmeyer counting or like these other algorithms, yeah. But here, in this talk, I will talk only about exact contractions. Actually, no. So you can find pretty hard instances, but you are right in the sense that in the space of all instances, there's very few that are hard. Okay? But it so happens that there's interesting stuff happening where the hard cases are. Okay, so indeed, there's a whole other. So here we talked about NP complete, Sharpie complete, etc. This is one way of classifying problems, and it's the worst case classification. We could also talk about average case complexity, and there are problems that are worst case hard, but average case easy. Okay. What I'll be talking about are these horrible problems that there's no approximation. They are just, you have to live with it. Like there's no way that we know, and there's likely no good approximation scheme. Okay, that concludes the part on basically the menu items 1 and 2. Now I would like to get to contraction. I should do this here. Okay, so we saw, yes. Yeah. Oh, yeah. Totally. Yes, so here's how you do it. A or B. So here's A, here's B. Sorry, here's A, here's B, here's C. And so here is A or B, and here is not B or C. So I cheated. You put a dashed line, yeah. So for that's just for the notation, but of course, in the tensor network language, you by default have it, because you have your original tensors written, you put the entries of your tensors in the right way, and then you contract, and it automatically takes care of negations. You could, yeah, you could. Okay, now contraction. Time is, yeah, these extra minutes are really coming in handy. Okay, great. Contraction, we don't need that. So we say we have our tensor network, and so we will focus very literally on the word network here, which is a graph. So we have a graph, G, and mathematicians and computer scientists, they write graphs like this. V is a set, E is another set, which is a subset of 2 tuples of vertices in the vertex set. Okay, this basically means something like this, okay? In fact, for any tensor network, we can have any graph, but in our case, we'll have bipartite graphs also. So tensor contraction in the graphical language is just represented as a vertex contraction. You take 2 vertices and you lump them together. Okay, sorry, this I need to write here. That, just to be clear, this representation as tensor networks, I didn't come up with, but this existed, and this works by Attore and Diamonte that had this language already. So these people saw how to write these problems as tensor networks. But the problem always was, okay, I've represented them, now how do I contract? So that was the stumbling block, okay? Vertex contraction, then we have the contraction order, which is what we will be dealing with or path in the rest of this presentation. And this you can represent as a rooted binary tree. Rooted because we are considering full contractions without any free legs at the end. So this is our contraction tree. Okay, so we have a graph. We want to find a contraction order. And the question is, how do we do this? Of course, there is the typical cartoon that you see often, which says, just start bubbling. And then so you contract this, and then you contract that, then you contract this into the rest, etc. But if you try and do this in a greedy way, so you just look locally, you find something is very, very suboptimal. Okay? So again, these are all exponential time, but you find a path like this that is exponential, but also very bad. Okay, so this might trick you into thinking that the contraction that you want to do is impossible. But how do we parameterize? How do we rank these contraction trees? Okay, in other words, what is the precise metric that tells us that a contraction path that I've chosen is actually good or bad? Okay, I need a figure of merit. And so, what is this figure of merit that defines my contraction costs? And so, if you care about memory, it turns out it's something called edge congestion. If you care about runtime, assuming a typical tensor multiplication cost, then it's something called vertex congestion. And I want to show you, intuitively, these are easy to understand, but the jargon is a bit difficult. So what is edge congestion of a graph G? It is the minimum over all tree embeddings of G of the maximum edge or vertex congestion. Okay, so this is a mouthful. So what is a tree embedding and what is the minimum of the maximum, etc.? So I guess the best way for me to show you what this is to do an example. And I have a more complicated example later on in the slides. So let's do a simple example, because even if I write down the definitions, I don't think I can make it very clear. But in pictures, and let's do edge congestion because it's simpler. And I'll need colors for this. Okay, so here's a tensor network example. Okay, so okay, here's my tensor network. Now, let me take let me take a binary tree, which is with which I will build my tree embedding. What is a tree embedding? Tree embedding means I take the vertices of my actual graph and make them leaves of a tree. Make them the leaves of a tree. So here I put U, V, W. Now let's pick a tree. Here's a binary rooted tree. Okay, that's my tree. And now what I do is basically I stretch the edges of the original graph such that they go over the tree. Okay, very scientific explanation, but actually it's simple. So you between V and W, I have an edge, okay? I have the red edge, pink, whatever this is, okay? So I connect them like this, spanning the edges of the tree. Between U and V, I have a blue edge, and so I connect them like this. And then between U and W, I have a white edge. Connect them like this. This is a tree embedding of graph G. This is graph G. This is the tree embedding onto tree B. And now what is congestion? So you see this tree has 4 edges. 1, 2, 3, 4. Edge congestion is the following. Okay, B is a graph also, so it has a vertex set and an edge set. So I maximize over the edge set. What? Log 2 of the number edges of G spanning edge E. Okay, so here the edge is the edge of the tree, and the number of edges that span this edge are the edges of G, my graph. What does this quantity tell me? Basically, you can see the contraction as going up this tree. So if I cut here, for example, I have done one contraction. I've contracted V and W together. Okay, and the edge congestion of edge number 2 tells me how many legs I have in the resulting tensor. Okay, so it tells me the size. And so maximum of these is the maximum tensor I will ever, the maximum size tensor I will ever need to build throughout this contraction. And so then what do I do next? Next, what I do is I can build a space optimal contraction tree. For graph G, which is of all possible binary trees with, say, leaves being my vertices of the original graph, take the one that gives me the minimum congestion. Okay? Yes, thanks. So that's awesome. That's where I was going. So first of all, similarly, I can have a time optimal tree, contraction tree, and funnily enough, these two are not always the same. Okay, so you can aim for space or you can aim for time, and it's not always the same thing. Okay, it can be different. Problem is, calculating this is itself NP-complete. So you're trying to solve a hard problem, and in order to solve it optimally, you need to solve another hard problem. Okay. So what do we do? And apart from the fact that it is NP-complete, of course, there's heuristics for NP-complete problems. But actually, sorry, this is not NP-complete. It is actually NP-hard because the space is larger. Space of all trees is larger. But in any case, it's a hard problem for which we don't even have good algorithms. Okay. That's it. Yes, yes, yes. Okay, so what do? We do heuristics, okay? And what I would like to do in the next minutes is show you some of these heuristic algorithms that we came up with. Okay, so now I need to, yes. We need to switch the, okay, okay, good. All right, so, can I use this? Sorry? Oh yes, the time, okay, I didn't define it, but this one uses the vertex congestion, which is basically edge congestion looks at the edge. To get the time complexity, you look at the vertex, because the vertex, if you look at it and think about like 2 minutes, you will see that basically the number of legs is like the log of the dimensions that you have to multiply to actually do the contraction. Yes. Yes. Yeah. Okay. So no, this can stay there. Okay. What do I have here? Okay. Yeah. So some simple, very simple examples to show that it's sometimes, I mean, to show the general fact that the order of contraction matters, okay? So this is like really trivial stuff for you guys, but suppose you have a ladder, you can really shoot yourself in the foot if you try to contract it in the wrong order, but in this case, finding the order is trivial, right? So if you contract the legs first, you get humongous tensors. If you contract the rungs first, you're good to go, okay? And so, okay, here's a more complicated example. You have to contract this tensor network. Okay, and you might go about contracting these two first, and then these two, and then these two, and be done. Or you might contract these two first, and these two first. These are two local greedy algorithms of doing it. And there is a difference, right? Especially in memory, in terms of memory, because here you generate a rank 4. Okay. Just simple stuff. So what do physicists do? Usually when they have a problem, they try to avoid it. And so there are algorithms where finding the optimal path is really trivial. So cases like the DMARG algorithm, where you need to contract objects like this, are pretty simple. And in fact, in most cases, as we know, you don't even need to contract this full thing. Okay. Other cases that are simple are 3 tensor networks, where you just contract from the leaves up and you're done. Okay. There's less trivial examples. Okay, I shouldn't be showing you this, but so in higher dimensions, you might be doing things like coarse graining. Coarse graining is in general a good idea many times, especially if you can do approximations, and then you end up with a self-similar structure, and you keep doing this over and over, and sometimes it works. Okay, there are other cases. Okay, I'm just showing examples here. Last week we had a discussion about continuous MPS, and there's a formula for like grid structures where you eat up the lattice gradually, and you're good to go. Now, what I'm interested in are these sort of problems, where your tensor networks look like a mess. And it's even worse. It's not a complete mess, but there is structure, but not quite. Okay, so these are two examples that I show here. The first is just quantum circuits, and in particular, these experiments on random quantum circuits in order to achieve something that is hard to simulate with a classical computer. Okay, and so because these circuits are, well, random, and because the gates are picked up from a gate set that sometimes you can resolve easily locally, you get networks that look like this. So they have some structure, but not quite a lattice structure. You might also want to simulate other quantum algorithms like quantum machine learning. And in this case, you get networks like this. to simulate your variational circuit ansatz. So here we are faced with a problem of coarse graining irregular networks. There's a number of ways to do it. There's an overview of all of these in this second paper. Things that were known before were, of course, exhaustive search, which doesn't work if you have more than, say, 10 tensors in your network. Greedy bubbling, which is what I sketched there, which is also very suboptimal in most cases. And you also have this tree decomposition of the line graph of your network. And so this, you take your network, you build another graph out of it, and then based on some decomposition of that graph, you come back and you have a contraction order. And that was known from the work of Markov and Xi, if I remember correctly. But again, this poses technical challenges when it comes to be implemented as an algorithm. And so then, at that point, when I started looking at this problem, this is what was mostly known. And then these are methods that I came up with, and then greatly expanded upon by Johnny Gray, which was my collaborator in that work. And on top of using these techniques, which I will sketch in a second, to find the contraction trees, you can do other things like slicing your tensors or hyper-optimized parameters, etc. But here, I want to show you a cartoon of how this works. 8 minutes, fantastic. Okay, so graph partitioning. So the idea here is as follows. Imagine this is your network, and okay, this looks like a petri dish, but basically these are tensors, and the gray part you can imagine is some density of edges, okay? Some density of bonds between your tensors. So how can I coarse grain something that is basically has a very little structure? So here's one idea. Let me try to actually cut my graph in half in a more or less balanced way. What does it mean? It means I want to find a cut that is as short as possible across the graph, cuts it in two, but at the same time, cuts as few edges as possible, and the two parts are roughly equal. Equal number of vertices on each side, okay? And so let me try and do this hierarchically. So you do a big cut across the graph. So I cut it in half. And now I take the halves and cut them in half. And then I take the quarters and cut them in half. Yeah, so I assume I drew a graph. It looks like a mess. So instead, I put like this gray area to represent like a density of edges. Anything is connected. Yes. Oh, randomly. Yes, because you're not looking in a space that has any planarity in it or anything. Yes. Well, not randomly. You use heuristics to cut it, to achieve this balancing that I said. So you cut it in half such that you cut as few edges as possible, but you have two pieces that are roughly equal. That's balanced graph partitioning, okay? And then you do this iteratively until you reach the individual tensor level, okay? And then what you do after you've done this is you contract backwards. So you take the smallest neighborhoods you've found, you contract them together, okay? What does this achieve? In this whole hierarchy, I have made sure that the cuts are as short as possible, meaning they cut as few legs as possible, okay? So it means each of these cuts here cuts as few legs as possible. So it means that this tensor is as small as possible. Okay, so this is a proxy for minimizing this. It's a proxy, okay, and this is a heuristic, but it actually achieves this, and it achieves it quite well. And so, sorry? No. Sorry, this is just for you. This is just to make a cartoon. I'm not assuming anything. It can be anything you want, right? So the only rules are, here's a graph, cut it in roughly half, equal parts, cutting as few edges as you can. That's it. That's the name of the game. Okay, no planarity. Yes, that's also NP-complete. Yes, indeed. So minimizing the cut width is NP-complete also, but there are good heuristics for it. That's the difference. So for this sort of problem, we have a long history of, because this is a simpler problem. It crops up a lot in graph theory, okay? Whereas this is very esoteric, okay? Yeah, thanks for the question. And so you keep contracting, and at each level of the coarse graining, you have made sure that your tensors are as small as possible, okay? So you contract until you get the answer, okay? So, yeah, so this is a different example of a contraction tree where you see that in one case you get an edge congestion that is smaller than the other, but that's not very important. Can skip over it. Okay, so applications. Here's the SAT formula example that I showed you before. These are my copy tensors. Here I've done it the opposite way. Sorry about this, but this is my delta tensor that represents the variables. Here are the constraints, and here's how the problem looks like. And you want to evaluate how many assignments satisfy a formula using tensor network contraction. So here's some performance benchmarks for two particular problems. There are vertex covers. This is basically 2SAT, and this is some other harder problem. Here I plot median runtime on a log scale versus number of variables in both cases. And so this mini C2D is the best counting solver that I found for these problems, non-tensor network-based solver. And these are benchmarks for the various methods. This METIS is the hierarchical graph partitioning that I showed you. Greedy is greedy, and GN is some other method based on community structure. And what we find is that in both cases, here we are not beating the best algorithm in relative terms, but in absolute gain. The size for which this will beat our algorithms is for computations that are several times the lifetime of the universe. And in this case, we beat also in relative terms the performance of the best solver. And in fact, this makes feasible computations that were totally infeasible before, okay? So in fact, for this problem, if we add weights, there are actual competitions. People come every year and duke it out. They bring their best algorithms, they have instances and they test them. And so we just took we didn't take part in the competition because we just wanted to publish a paper. And, but we took the instances of the championship in 2020, and we compared with the performance of the winner of the championship, okay? And so the champion solved 69 out of 100 instances within a certain timeout, and our solver solved almost all of them. It had trouble in these particular instances because these were the more difficult structures. And here you see this thing that I was saying. You see some structure in some cases, in others not, okay? But we solved almost all of them, and there was one very hard that we weren't able to solve. Yeah, I guess so. If you, if you're unlucky and you pick the one here, you might give up, right? So. No, the benchmarks, you time each individual problem independently, right? The smallest? Yes. No, you do all of them, yeah. And also in fact, this can give you also interesting insights because for different solvers, you don't get the same, the easier problems are not the same for each solver. So if you build a meta solver of choosing the right one for the right problem, you might actually have a benefit. Okay, and so last thing I want to show you are these benchmarks for quantum simulation. You don't need to, you guys all know this, but basically you write your quantum circuits as a tensor network, and then you try to contract that network. And so we took these Google Sycamore circuits from this publication from a few years ago. And so it's this graph here. Here I have this contraction cost as we evaluated using this, B time. And so here, this is again in log scale. This you can imagine as some, as flops times a prefactor, okay? And this is cycles. Cycles means the depth of the circuit. So each cycle is about, if you think in trotterized terms, is like 4, depth 4, okay? So this is deeper than it looks. And so here are the different methods. These are all, apart from, I think, this Q-flex, everything else is a tensor network approach. But this Q-flex thing is close to Google's estimate for how long this contraction takes. And the rest are our methods. Well, QuickBB is the line decomposition, line graph decomposition, so it's not ours technically, but, and FlowCutter is the same, but BigGreedy, GN, and KHypar are the ones that you can find in this paper. And so you see that basically you get several orders of magnitude improvement. And in fact, the estimate for Google's estimate for this simulation using the entire supercomputer summit was 10,000 years. Our estimate is 195 days. People later on showed that it would take 300 seconds if you had a bigger supercomputer. And then using various improvements on our methods, the group from Beijing actually showed that you can do it in 15 hours, okay, on some number of GPUs. So this field moves fast, okay. Yeah, so this is just another, it's not just for random circuits, but this is an energy evaluation for a quantum algorithm called QAOA. And what we show here is because of some weird effects in QAOA, if you don't go to deep enough circuits for your QAOA, basically you can simulate anything on your laptop. Implementations of this code can be found either by my collaborator or NVIDIA, which have now implemented these algorithms. And here in yellow is the performance for the code developed for our paper versus what NVIDIA does. And you see it's basically very close, but they improve in other ways. You can use these methods already. Conclusions. Finding a contraction path is in general hard in the worst case, but in average case, it's actually good enough. Even if you find the best contraction path or a near optimal contraction path, your algorithm is going to be bad, okay? It will scale exponentially, but exponential and exponential can be very different, okay? And so this enables you to do much larger simulations than people thought possible. And so this means you can simulate quantum circuits and also solve computational problems using these techniques. These are directions for the future. These are the people who fund us, and that's it. I'll take any questions you have.